Hello, we will continue our study of physics today and discuss physical quantities that are described not only by their numerical value but also by their direction. As you and I are aware, physical phenomena and parameters of objects are characterized by various physical quantities which we explored during our examination of this subject. All physical quantities can be divided into two major groups. The first group consists of quantities that are solely characterized by their numerical value, while the second group includes quantities that are characterized by both numerical value and direction. Therefore, we refer to the former group as the quantities that are solely characterized by their numerical value. Scalar quantities. For example, such quantities can be mass of a body, i.e. the value that actually determines how much substance is in this body, and of course it has no direction. A quantity such as the density of a body, let's say temperature, volume, and so on. That is, these are quantities that we characterize only by numerical values. However, it is important to acknowledge that in different life scenarios, there exist magnitudes that necessitate not just numerical assignments, but also consideration of their directional aspects. Let us consider such a situation. You are in an unfamiliar city and you need to go to a movie theater. I approach a stranger and inquire about the cinema's location. The response I get is that the cinema is situated at a distance of 1 kilometer from where we are currently standing. Of course, this information will not be enough for you to find the movie theater, because you can move in different directions, go 1 kilometer away, and it is not a fact that you will come to the right point. Therefore, in order to successfully accomplish this task, you need to clearly know not only how far away the object is, but also in what direction you will need to move. Therefore, a number of quantities of physics will be characterized not only by a numerical value, but also by the direction as well. Such quantities we call vector quantities. And to these quantities we can refer the displacement of a given body. Just it shows how much and in what direction the object moves during some time. Such a quantity is velocity, taking into account its direction, acceleration, force, and so on. That is, wherever such a quantity has its direction, we will necessarily denote it by the corresponding letter and the vector sign above it. Therefore, when we talk about vectors in physics, of course we should know not only that there are such quantities in physics, but also understand how to work with them correctly. So today you and I are going to learn some of the mathematical possibilities that we can apply to vectors, particularly physics. What is a vector? Once again, let's look at the figure. A vector is a directed segment. That is, this segment has some length and plus is given by the direction. A vector is denoted by some letter. So let's say it will be vector A, and it has a certain direction. In order to solve problems, it is important to understand that scalar equations cannot be solved using vector quantities. Hence, when working with vector quantities in problems, we need to consider the relative position of the vector in relation to the chosen direction. Let's suppose vector A is currently aligned along the horizontal x-axis, which serves as our coordinate axis for determining its position in space. In this particular scenario, it is essential to acknowledge that vector A possesses a component. Specifically, it holds a projection component on this axis, one that we have the ability to ascertain. By constructing perpendiculars to the given axis, and then we obtain the component of the given vector on the given axis. We denote it by the letter A with the index x. In order to determine it, we need to know the coordinates of the beginning of this vector and the coordinates of its end. Then the difference between these coordinates will give us the length of this projection, this component. Then, of course, we can also talk about the projection on the second axis, which is the y-axis. And in the same way, we must drop the perpendiculars on the corresponding coordinate axis, and we get the component along the axis y. This will be our AY. Also, to find it, we must know the coordinates of the beginning and end of this component. Let's look at an example that will allow us to understand how to determine the components of a given vector, taking into account the knowledge of the angle at which the vector is located to the corresponding axis. For example, we draw the x-axis horizontally and we place vector A at some angle to this axis. And if we know the angle at which this vector is located to the x-axis, we denote it by the letter θ. We get such a figure, from which we can further build the components of this vector. To do this, we lower the perpendicular to the corresponding axis and see that we have a right triangle in which the hypotenuse is the vector itself and the cathetes are the components of this vector. The horizontal cathetus is AX and the vertical cathetus is AY. And in order to determine this cathetus, we can use simple trigonometric relations in which the sides of a right triangle and the angle of this triangle are related. Let's look at finding the cathetus AX. In this case, we see that it is an adjoining cathetus for the angle θ. We can connect it to the hypotenuse through the cosine of this angle. Therefore, the value of this cathetus will be defined as the product of the vector A itself by the cosine of the angle θ. In this case, of course, we are talking about the modulus of this vector, that is its numerical value, and we find thus the magnitude of this component, its numerical value. In the same way, we can consider the calculation of the value of the component on the y-axis, and in this case it is the opposite cathetus, which we can find already through the sine of this angle. So in this expression, we reflect exactly the sine function. And in this way, we have obtained the calculation of the two components of these vectors, depending on what angle this vector makes with the given x-axis. Now let's see how these components can allow us to calculate the vector itself, which consists of these components. We see that we have a figure called a right triangle, and of course, we do not forget that there is a theorem that allows us to connect the sides in this triangle. It's the two cathetes and the hypotenuse. It's the famous Pythagorean theorem. Let's write it down. This is how it will be written down, and then we can calculate the vector A itself as the square root of the sum of squares of the components of this vector. We will also use this rule quite often when we need to find the vector itself, knowing its components. What other operations can we perform with vectors? Not only can we find the components of vectors or vice versa, but we also encounter situations where we have multiple vectors in one problem. For instance, consider a moving object that has been traveling in different directions. In order to determine its total displacement, we need to consider all the individual movements and add them together. By doing so, we can calculate the overall displacement of the object. Let's examine an example to better understand this concept and determine the rules we can apply to accurately calculate the sum of vectors. Overall, there are multiple operations we can undertake with vectors beyond simply finding their components or vice versa. Suppose the body has made a displacement of magnitude S1 moving in this direction, then has moved by the value S2 in this direction, and let's say it has moved by the value S3 in this direction. That is, we can know all moduli of these displacements and know their directions, and now, in order to determine the total displacement of this body, we must add vectorially all these values. That is, mathematically, it will look like this. The total displacement is the sum of all the displacements that this body has made. And of course, we're talking about vector summation. How to perform vector summation? In this case, when we're talking about the addition of many vectors, it's very easy to construct it when you construct all the given components of the sum in sequence. That is, you combine the beginning of one vector with the end of another vector. The final sum will be determined by the vector that connects the beginning of the first vector and the end of the last vector. That is, this is how we build with you the vector of movement of the total. These are vectors that we add sequentially with each other using the polygon rule. That's what it's called. The given rule can be simplified to the triangle rule. If you are combining two vectors, rather than a set, we can illustrate this scenario graphically, which is S1, S2. And that's how we build this figure up to a triangle, and we get the final displacement of this body. The concept of a parallelogram can be used as an analogy to this rule. To demonstrate this, we can merge the starting points of both vector components into one point. In order to accomplish this, we can utilize the property of vector displacement. A vector can be moved from one location to another without altering its direction or magnitude. To illustrate this, let's consider moving vector S2. By doing so, we can effectively demonstrate the rule. To align its origin with the vector SI for enhanced alignment. This is roughly what this picture will look like. Then, in order to determine the sum of these vectors, we build this figure up to a parallelogram. Based on the two vectors we already have, and we build the diagonal of the figure. And it is nothing else than the final displacement of this point. Triangle rules and parallelogram rules work identically. That's why you can choose which of these rules you will use better depending on the situation. Somewhere it is sometimes convenient to use the triangle rules, somewhere it is convenient to use the parallelogram rules. And also, of course, we can not only add vectors, but also subtract them. That is, the difference of vectors is in principle the action of the inverse sum, so it can also be considered on the sum triangle, only turning one of the vectors in the opposite direction. Let's say we need to subtract vector b from vector a in order to get some vector c. In the figure it might look like this. So we have vector a. And I draw vector b from the same point. That is, for convenience, I combine their beginnings. Accordingly, vector c will be a vector that will connect the ends of these vectors and will be directed towards the vector being reduced. The vector to be reduced in this case is vector a. Therefore, we connect the ends of these vectors and point the final vector c toward the vector to be reduced. This is also the triangle rule if we are talking about the difference of vectors. Depending on the problem, of course, you will look at what you need to do with the vectors, sum or subtract them, depending on where and how they work. In practice, you and I will see how these transformations work. That's the end of the lesson for today. Goodbye, everyone.